Yeah, I'm really excited to be here today. Thanks so much for the invite. I'll share my slides in a minute, and I just wanted to make a plug for anyone who's going to CVPR. Um, Actually, Paula and I are organizing a workshop and a tutorial at CVPR. So if you're going to CVPR, please consider checking it out. I put the link up in the chat there, and would love to see you at CVPR at our workshop and tutorial. Okay, I'm going to share screen. Okay, I'm going to go into slideshow mode. All right, can everybody see that?
See and hear loud and clear.
Excellent. All right, so today I wanted to introduce you to some of the things that John Deere is doing with deep learning and robotics, and how we're looking to transform agriculture with, primarily deep learning and transformers. I want to set the table a little bit with why we think this is an important problem to work on. So by 2050, it's kind of an incredible statistic, but there's going to be 10 billion people on the planet, and there's going to be 50% more demand on food. So if you take the food demand today, projected out to 2050, even by the most sort of conservative estimates, it has to grow by 50%. If you add into that equation the extreme variability from climate change, what we see primarily, John Deere is a global company, do a lot of business, obviously, in the Midwest. What farmers are seeing there is that their average rainfall is roughly the same as it was, a decade ago, but they're getting it in floods and droughts and floods and droughts. And there's just a lot of variability, which makes farming, very, very tough to do when you're working in a extremely variable environment. Add to this labor shortage, aging workforce. Average age of a farmer in the U.S. is 56 years old, and it's kind of another kind of really amazing statistic is that the farm jobs, sort of in the next decade, are only going to grow about 1%, and those actually might be fairly optimistic. So there's very, very low, almost zero job growth predicted, and probably going to be job loss is our prediction. And coupled with extreme variability and growing population, this is a huge set of challenges for farmers across the world. Deere's approach to solving these problems used to be bigger, faster, stronger. Bigger means larger machines, which plant more rows, like 32 rows at once instead of 16, so you can do your job faster. Tractors with more horsepower are stronger, so they can pull larger equipment, which is bigger, and deeper plows, if you like. So bigger, faster, stronger was kind of the playbook for decades, actually, and all the big ag companies really have followed this in one way or another. But we think that this playbook is probably run its course, and the next set of our next playbook looks like automated, easy to use, more precise. And so I'll talk a little bit about the automation precision today, and I'll show you a couple of the new products that we just launched. One thing that's really kind of really earth-shattering here with working with John Deere is that currently there's 800,000 John Deere connected machines, and collectively they traverse, a third of the Earth's land surface on a yearly basis. So making impact at scale is something that John Deere is very well positioned to do. And that excites a lot of us at John Deere and Blue River. I should have mentioned I'm a Blue River employee. Blue River is a wholly owned subsidiary of John Deere. We were a startup and we were acquired in 2017. And now we're working on the John Deere product line, bringing AI to that product line. So, if we can improve the performance of something by, say, 2 or 3%, that can actually have a huge impact just because John Deere has this enormous global scale. So I'll show you a video right now. This is the See and Spray system. And what you're looking at is called a self-propelled sprayer. It's a huge machine. It's 120 feet long from the boom that you can see there with the yellow tips on it. That's 120 feet long from tip to tip. And what it's doing is it's going through row crops. We support 3 row crops, corn, soybeans, cotton. And what it's doing is doing spot spray or precision spray. And you can see that if you look closely at the nozzles, not all of them are spraying, just some of them are spraying. And the reason it's doing that is because it's only spraying when it detects weeds. So you can see that pretty clearly here from the side-on view. So fun fact, this product is in its 3rd year of customer sales. And last year alone, it saved 8 million gallons of herbicide from being sprayed. So 8 million less than would have been sprayed normally. If you know a lot about farming, you'd know that the current state of the art without a See and Spray or spot spray system is that you would spray the whole field. So, if you had 100 acres, you would spray 100 acres. And typically you'd use GMO crops. So you can buy seeds from Monsanto and Bayer and Syngenta, all the seed companies. You buy seeds that are herbicide resistant. So you could spray Roundup, not hurt the crop, and then kill the weeds. That's sort of the normal way of farming. So with the See and Spray system, though, you can actually intelligently spray only when you see weeds. And this is done with 36 cameras on the boom. You can see these little triangular features here. These are actually protectors, so we can mount and look down at the crop. There's 36 of them. We have these hardened compute modules. So these are something that we developed in conjunction with NVIDIA. There's 10 GPUs on this machine, and it's capable of something like 0.3 petaflops, so 300 teraflops on your agricultural machine. I like to call it the smartest agricultural machine on the planet, and I think I'm not wrong when I say that. We have the nozzle technology is called Exact Apply, and there's actually 6 nozzle bodies here. We have a dual tank mode. If you look closely at the tank here, it says 1 and 2, and farmers can actually spray 2 products at once if they like. So they can use the front nozzle for See and Spray on a more expensive chemical, and they can use the back nozzle, for a less expensive chemical to broadcast if they want. The far more popular feature, though, is to use combined tank mode, where you just use the whole 1,200 gallons of See and Spray. And that's where the customers find most of the savings that we get. So just delving into the ML side a little bit, what we're using here is a segmentation model. It's a custom segmentation model that we built. It uses, basically a ResNet-like architecture, and takes in a picture of the picture of the crop, runs it through the model, identifies the weeds in the crops, and then we map that to the ground as closely as we can, given the height of this thing is called a boom. This black thing, the height of the boom is measured, and also we know the attitude of the boom. So a huge 120-foot carbon fiber thing is actually moving quite a lot during the field. So we measure the yaw, and we have gyros on here to kind of measure the position of that, and the whole goal is to really accurately map where that location of the weed is on the ground. And then we turn a sprayer on. So there's 99 individual nozzles, and we can turn those on individually if there is a weed in the nozzle's field of view. So really cool system. The farmers really like it. It's the third year on the market, and it's really making a huge impact. I think we're expecting to break kind of 100 million, 100 million gallons of herbicide saved next year, or like this year, I guess. We, as we go through the field, we actually record what's going on. And so here's a good field where the gray color indicates no spray, and then the color between yellow and orange and green, you can see that these indicate different levels of spray. So green being the highest and red being the lowest. And one thing you'll notice here, if you look at the savings, this is 62.8%. So this is a huge deal, right, for farmer, because just to kind of give you some numbers on how much it would cost to spray a field like this. A typical cotton farmer, say 5,000 acre cotton farmer, they're going to spend about $400,000 on seed, and they're going to spend about $150,000 on their entire herbicide program. So if we could put like a 62.8% dent in that, right, that's money back in your pocket, and you still get very good weed control with the system. So I'm going to deep dive a little bit on the computer vision part of this. This is the part that I worked on personally. I was the director of machine learning for the See and Spray program, and I was the first ML engineer on this project. But one of the biggest challenges we had to solve was dust. So if you look in the upper left corner there, you can see that the dust, obviously obscures the plants. And that's a huge problem because all fields are dusty, and it's a problem that we absolutely have to deal with. So, how do we solve this? Well, if you look at the bottom animation there, you'll see there's a couple of GIFs. There's one with no augmentation and one with fog augmentation. And the colors are green shows crop and red shows weed. So if you focus your attention on the bottom left panel just for a second, what I want you to notice is that when there's no fog, it's actually pretty good. But then as soon as the fog comes in, disaster strikes, right? And the crops the weeds turn into crops, which is a disaster because our system won't be able to understand, like, oh, I should spray this, right? And so from the farmer's point of view, this is a huge deal, because if our system gets fooled by the dust or the fog we did a little fog machine here to kind of test this, but this is a huge problem. So how do we solve it? Well, we actually developed our own dust augmentation. So we kind of started with ImageAug and used the augmentations there, and they didn't really help very much. So what we did was we modeled how dust can appear in an agricultural image, and we built a custom augmentation off of that. And those results are kind of shown in the right side. So now in this case, we're actually seeing a lot better. The model's much more robust to dust, still not perfect at all. And of course, if there's too much dust, it becomes completely opaque and you can't see anything. And if you can't see it, you can't spray it. So how do we handle that? Well, what we did was we built a predictor to tell us like how much dust is in this image. And if it's above a certain threshold, the safest thing to do is to just turn the sprayer on, the primary goal being not missing weeds. So that was one thing that I think was really important for us to solve. And we saw the customers in the early testing were like fairly disappointed by the dust performance, and we worked for a while actually trying to improve that. And in the end, we were successful. It just took a lot of work to get our dust, dust augmentation to the point that it was useful for customers. So, just if you're sort of working on things like this, right, make sure that you put a lot of effort into handling these edge cases, because in our case, it's not really an edge case because it happens in every sprayer, every field. So we had to put a lot of effort into this. We also predict low light, so and also motion blur as well. So we have our segmentation model produces segmentation results, and then it produces low light and blur as well. And so we're simultaneously estimating this. for every frame that we take. Okay, I'm gonna have to speed up a little bit because I think I might have spent a little bit too much time talking about the sprayer, and I do want to get to the automated tractor. So this is a picture of basically an 8RX tractor. That's the model number, and it's pulling a plow. And if you look carefully, you'll see that there's actually nobody in the field during this operation. So this is completely autonomous. And the way that we've solved this problem is we've chosen not to solve the problem of getting the tractor from like the shed to the field. So we've punted on that problem for now. What the farmer does is they they drive it themselves to the field. Once it gets to the field, they hook up the plow, the chisel plow on the end there, and then they take out their phone and then they can program a tractor through an app that we give them. And what they're doing is they're geofencing their field. They're saying, okay, here's the regions I don't want you to go in my field. Here's the boundaries. And then they press go. And what happens is we have a 360-degree computer vision system outfitted on this tractor. This was just launched actually this year. So this is the first year that it'll be in the market for customers. It's been tested in the market with customers in the Midwest for the last 3 years and during customer pilots. And every year, we believe really strongly in getting the technology out there to the customers early, gathering feedback, and then incorporating that in the next version. So we've been testing this for 3 seasons, and this will be the testing with customers for 3 seasons, testing longer than that. But this will be the first year that it's available to customers in general availability. Oops. Okay, so here's some views from the camera. So the top side here, I mentioned sort of 360-degree coverage. So the top the top row is the front, and the bottom row is the back. So you can see in the top row that we just put like some object in the field and see like, okay, does it stop? And the answer is yes, it stops if it finds an object that it doesn't recognize and feels like it should stop for. So this is how the system works. It's supported by a teleop system too. So in this case, the tractor would stop, a message would go up to the cloud, teleoperation operator would analyze and say, okay, is this a false positive? Is it a true positive? It's a false positive. They can clear it and the tractor can continue. If it's a true positive, then the farmer has to intervene. And so they would, get a notification on their app, say, hey, somebody's standing in front of the tractor. And, we're not going to move until they move. So then the farmer would go and clear the obstacle out. The bottom row is really interesting here. You can see how much dust. I mentioned like dust is a problem. Every field, every image, right? That's what I was talking about. And it's a huge problem with tillage because you're actually putting a plow into the soil and tilling the soil, right? So dust is a big problem in ag, as I'm sure you've probably guessed by now. Okay, here's some more sort of graphics from the computer vision system. So the top one here is the sort of true color picture with an obstacle shown with a little triangle. And the cameras see the obstacle. This middle one here, these are the depth maps that we get. So we spent a lot of time actually generating good depth maps. So we started with semi-global matching and that did reasonable, but got really confused on the sky and trees and things like that. So then we moved to kind of our own algorithm that we read about in the literature, where it's a semi-supervised algorithm where you train, given a stereo pair, you train the model to sort of replicate the right, like given the left frame, replicate the right frame. And that actually ended up working a lot better. So that's what we use. And here's a classification map that gets shown. You can see green is sort of drivable ground. Red is the trees and blue is the sky. And then yellow is sort of an unknown object. And then this panel here is the confidence maps on each of those, or the error maps. So just a kind of a quick look under the covers of the computer vision system. Last time I checked, we have over 1 billion images that we've collected from our test implements. As we build a training set for this problem, we've collected over 1 billion images for this project already. So looking ahead, Deere's goal is very ambitious. We want to bring autonomy to corn and soybeans by 2030, and we've got a good start. We've got autonomy in tillage by 2024, so we've started this process. But there's actually planting, there's spraying, which we're not doing autonomously yet, but that's sort of on the roadmap as well, and then harvest. So we've got a good start on this roadmap, but there's still a ton of work to do. So I think I'm going to wrap up here just in the interest of time, but hopefully I've managed to convince you that ag is something you really should care about. I like to say, a lot of people sort of underestimate the impact of ag on your life, right? Like, how does ag impact my life? It's like, well, I'm an out farmer, so how does it impact me? And I like to say, well, are you wearing clothes? And usually the answer is yes. And then if you think about where those clothes came from, it came, probably from some cotton farm, right? So farming definitely impacts you, and especially if you have eaten today or you're planning to eat, there's definitely a huge connection, right? So ag is a huge impact on all of our lives, and there's some huge challenges in ag. I mentioned the labor shortage and the increased food demand and extreme variability by climate change. These are all things that we need to do basically more with less, and we need to do it more efficiently. And we think that bringing technology to bear on a lot of these problems is the way to go. All right, with that, I think I'll wrap up and hand it back to Jimmy.
All right, but before you go, two things. First of all is I did repost the link to the CVPR challenge that Chris is spearheading. So the link is there if you want to pursue that. If you've got time for a few questions, I think we have a few here. I don't think they're going to grab on any sort of trade secrets or anything, but you let us know if they do. A question that we have is, are the cameras used RGB or also multispectral?
Yeah, very good question. So we do use multispectral cameras. We don't disclose the exact sort of band wavelengths, but we do have cameras that are very good at determining the health of vegetation. So that's pretty much all I could say on that. But yes, the answer is multispectral.
Another related question is, can we use infrared or ultraviolet band images to remove dust?
Oh, yeah, very good question. So it all really depends on the wavelength of the light and the size of the particle. So one thing that's really interesting from a job I had actually before working at Blue River, I was at Digital Globe Technology, which is now called Maxar, but they launched a satellite that had SWIR bands on it. SWIR roughly goes from like 1100 nanometers to say 2400 nanometers. And if you search actually LA fires SWIR imagery in Google, you'll probably find some images that are from that sensor. And what you'll notice is that the SWIR can actually see through smoke. And the reason it could see through smoke is the particle size compared to the wavelength of the light. So the particle size of smoke is fairly small and obscures completely in the RGB. But in the SWIR, the particle size, the wavelength is longer, and smoke is roughly transparent to SWIR, not completely, but very close. And so you can search images like that from Maxar and probably find some images of the LA fires. So in order to kind of beat dust, you'd sort of have to do something similar. And the problem is you usually have to cool the SWIR sensors. And one of the interesting innovations of the compute module that I kind of glossed over, but it's all passively cooled. And I don't know about you, but operating a computer at sort of 120 degrees Fahrenheit seems like a really bad idea, right? But that's actually an environment that all these computers have to operate in, on a daily basis during the summer, and sometimes even a little bit hotter than that. So we don't have, if we were to try to just deploy like sphere technology on here, we'd have to find a system, like figure out a system for cooling that sensor as well. So there are some technical challenges for that.
All right, so we'll take two more questions if possible. The next question is around the data sets that were used to train the models. And I think you did comment a little bit about the 1 billion images that you had to process. But is there any color that you can give around what sort of data sets were used to train when you were looking to differentiate between what is actual crop and what is actual weed? Were these proprietary data sets, or did you grab things from the public space?
Yeah, great question. So when we started the project, what we thought is like, okay, we're going to get yellow V8 and then fine tune it. And we quickly realized that because farmers want to go very fast when they're operating in their field, it's all about efficiency and productivity for them. So the faster they can go, the more they can get done. So our system, like the See and Spray system, actually works at 18 miles an hour, and it was very challenging to get to that level. And if you're thinking about in terms of budget, like compute budget or timing budget, that's like 4 milliseconds, per batch for us, right? Which is pretty wild on the computer vision side. So immediately we sort of decided, okay, we can't actually use any algorithm that's out there already because it's just not going to be fast enough. So we hand tuned our own network from scratch, and along with that, sort of came with okay, now we actually have to build a training set. And at the time, there wasn't any reasonable sort of segmentation data sets out there for ag. Now there are, though. If you go and search in Google for ag ML, you'll find Mason Earle's page from UC Davis, and he's curating like a really great ag ML data set actually for machine learning people in ag. So the situation has changed quite a bit actually since we started this project back in 2017 is when we started. So proprietary data sets, we spend a lot of time teaching people how to label these data sets. It's really, really tough. I think actually the biggest challenge on this whole project has been just managing label quality and making sure that we're giving the model unambiguous labels, which ended up being like a really hard thing to solve. So yeah, hopefully that helps answer the question.
All right, I lied. We'll take two more questions, but one of the questions a lot of people ask in a couple of different ways. But this next question is, how do you account for the lag in image and processing time? And the question is around how many frames per second can the sprayer run at? Are the nozzles on the camera offset to account for that? I'm assuming you're jamming down the field at a certain rate of speed. How fast do you have to be on the trigger to get the herbicide at the right place at the right time?
Yeah, great set of questions. So from like image acquisition to spray landing on plant, it depends on a number of factors, especially the height of the boom. But say at 24 inches off the canopy, we usually benchmark it at about 200 milliseconds from image capture to spray landing on a plant. And so that's pretty fast, right? It's 5 times a second. How do we design the system? And we use actually a couple of interesting techniques there. So if you think about like, this is like not going to be a very good demo, but I'm going to pretend my hand is a sprayer and then the nozzle is pointing forward. So if I'm trying to hit something here, right, I have to turn the sprayer on at some point before and then turn it off at some point after. And so there's a buffer system there, right? And there's some inaccuracy with, how we map the plant to the ground. It could be slightly inaccurate, so we can handle that with a buffer. And that means we have to turn it on like a little earlier than we normally would. Another trick we can use is something called a rear-facing nozzle. So if I have a rear-facing nozzle, then I actually can turn that on way later than if I had a forward-facing nozzle. I'd have to turn it on way sooner, right? So a rear-facing nozzle buys us a little bit more time, and that's one of the ways that we make our like 18 mile an hour spec is we say, okay, if you want to run faster, you have to put this nozzle in. That buys you like a little bit more processing time. We also lifted the cameras up. So if you saw those like triangle things on the boom, we did that deliberately, really for two reasons. One is it buys us more time, but second of all, it also helps us solve occlusion. So, if I'm if I have sort of like one of my cameras covered by a crop, there could be a weed behind it, right? But if I now move and I've got another camera, right, I could probably see that weed with the other, and I think maybe that did come across there. So if you're lined up completely here, you might not be able to see, but if you're at a different angle, you can actually see the weed. So that's why we do that, and that's why there's 36 cameras. You might say like, wow, that's a lot of cameras. Like, couldn't you do 16? And the answer is yeah, but we're going to miss that occlusion, and we're actually going to miss weeds that way. So that's why we designed the system that way.